So as you saw when you looked at 9.1, we have certain ways that we program machines to detect these errors. So the barcode codes that you saw in 9.1 had a specific pattern that went with them. So they added this extra digit at the end, and that was used to help identify any errors that happened during the scanning process. So for the zip code check, all the digits that we had with the extra digit summed to a number that was divisible by 10. So if we didn't have that check digit that summed to 10, the computer would know that an error had occurred, some sort of misread happened. So this idea of having errors that are happen with machinery just happen, and so we can program and kind of work with those errors to alert these users that these errors have occurred, and so that you can go back and double check. So that extra digit is also called a check digit, and again, it's used to help identify any errors that have occurred or any errors that are occurring while you're scanning your machine. So as I said, the zip code check digit was an extra digit at the end, and it made all of the numbers, including the check digit, divisible by 10. So, for example, if I was coming up with a check digit for this zip code, the first thing I would have to do is add them all together, which if I do add all those, I get 21. And so obviously 21 is not divisible by 10, but I have these 5 plus an extra, the check digit, to make it divisible by 10. So that would mean that the check digit for this particular one would be 9. So that 21 plus 9 is 30, and that's divisible by 10. For the next one, there's actually, I made an error when I did this. We should also say you kind of need this information, otherwise it could totally be valid, but this is part of the problem with the check digit being 2. So this machine originally reads the zip code as 48656, and the check digit that they read is 2. So if we're trying to decide if this made an error, we'd have to sum 4 plus 8 plus 6 plus 5 plus 6 plus 2. And so if we do sum all of those values together, we get 31, which is not divisible by 10. So yes, there was an error. So check digit is always there in the zip code. So we have a zip code that's originally read, but we come up with a check digit so that that zip code is valid. The problem with this zip code check, because it's pretty simple, all we have to do is add up the numbers and the check digit and see if it's divisible by 10. The problem with it is that it doesn't protect against all errors. It protects misreading a single number. So if that number 4 was misread as 5, it would protect against that. But it doesn't protect against any transposition of numbers. Meaning if I had this zip code, let's say that I had that zip code and that's really what I wanted to have. Let's say that the computer read, instead of 68601, it read 86601 with the same check digit as 9. This is an error in how the computer read this, but it still satisfies the check digits that's in place. These plus this extra digit, still sum to something that's divisible by 10, and this plus that extra digit also sums something that's still divisible by 10. So because the zip code one is a little bit simple, it doesn't protect against everything. It's probably good enough, honestly. They probably wouldn't read this transposition of numbers necessarily, which is why maybe it's still valid, but there are other issues that we run into, or other different types of detection models and scanning that we want to like actually be able to detect these a little bit better. So there's lots of different ones that go with it, with different or finding different errors, and there are different tests that can be performed, like the computer would perform, to make sure that these things are divisible. So we actually know some of these. Excuse me. We know some of these already. For example, if I know that something's divisible by 2, or an easy way to double check that something's divisible by 2, all we really have to check is that the last digit is even. So if I gave you 8,572, I would know that that's divisible by 2 because the last digit is even, or 8,566. 8,567 is not even. So that last digit's 7, not divisible by 2. So it's an odd digit. It's not something that would be, necessarily even. So that's a really easy way to tell. We don't have to actually check everything. We only have to check that last digit. And that happens with a few different things. So one way to tell if something's divisible by 3, I think I even mentioned this in class one day, but this is one of my, I think this is a kind of a cool trick, that if I sum the digits and I find that that sum is divisible by 3, then the whole number is divisible by 3. So for example, I don't know, 54 is something that's divisible by 3 because 5 plus 4 is 9. 9 is divisible by 3, so 54 is divisible by 3. So you can come up with lots of different examples, like right off the bat, 441 is not something that I would consider to be divisible by 3 without a calculator, but I do know it is because 4 plus 4 plus 1 is 9, and again, 9 is divisible by 3. So there's kind of that quick check to see if it's divisible by 3. And so that's one of the ways that we can kind of look for these divisibility tests. For 5, this one's also we kind of know this one, but the last digit is 0 or 5. So 10, 15, 20, all those things are divisible by 5. We don't have to check everything. We just have to check that last digit in order to see it. 9 is really similar to 3, actually. The sum of the digits is divisible by 9. So if that's the case, then the whole number is divisible by 9. For 10, the last digit has to be 0. And then 11 is actually kind of hard, so we're going to do a test for it to see without a calculator, but the test is a little bit complicated. So what we have to do is truncate the last number, the last digit. So we'll truncate the number by dropping the last digit. And then we do something kind of weird. We take the difference between the truncated number and the last digit, and that has to be divisible by 11. So I know that doesn't make maybe a ton of sense, but we'll actually see what that looks like here. So without a calculator, we're going to see if this number is divisible by 11, which if you do type it into your calculator now, your answer should be yes, but we'll perform this kind of series of tests to see it. So what they mean by truncate the number by dropping the last digit is that we're going to take this number and we're going to cut out this last digit 5. So now we're dealing with 9,751. And it says we drop the last digit, but then we take the difference between that truncated number and the last digit. So last digit was 5, so now I take the difference between that number and the last digit. So if I take 9,751 and I subtract 5 to it, I get 9,746, which again, right off the bat, I don't know if this is something that is divisible by 11 because it's still too big for me to tell, but that means that I can still perform the same test on it. So I can do this truncated thing again. So I'm going to drop the last digit and subtract the difference between them. So if I take 974 divided or minus 6, I should get 968. And again, same thing. This is not something I really know, but I can perform that test again. So I truncate, get rid of the last number, take the difference of it. 96 minus 8 is 88. And now, hey, I can know that that thing is divisible by 11. So this is a place where I know that it definitely is. So that would mean that 97,515 is also. Which I think is kind of a weird test, but it at least can kind of segue into what we're going to talk about next. I think this section and this next section, I think, are a little bit tricky. I think they're probably the hardest sections of this chapter because the next part that we're going to look at is confirming these divisibility tests, which is kind of proof-based. But the good news is that it's very algorithmic. So the process and the procedure in which we do this confirming is pretty much the same. And also there's not a ton of variability. So we have like a check digit or this divisibility test that we're going to prove for divisible by 3, and we're going to do it by 11, we do it by 9 or 4. And so there's not really that many variants in how we do this, which means that once we kind of get this idea down, the next step in the process for repeating it isn't too bad. So we're going to use algebra and kind of like a proof idea for how these divisibility tests work. And I have some steps here so you can follow for the next time that you do this. And we'll do it together like for this last example too, and so that we can actually look at it. So or like kind of like all together. So the first thing that we're going to look at is considering this 4-digit number, and the check digit is they're giving a divisibility of 3. So to decide if we are divisible by 3, what we really need to do is the divisibility test for divisible by 3. So we need the sum of the digits to be divisible by 3, or that's kind of like the known information. So if I know that the sum of the digits is divisible by 3 already, then I can represent A, B, C, and D, which is this 4-digit number, to represent the digits. And if I know that the sum of the digits is divisible by 3, I would add up the sum of these digits. And if I know it's divisible by 3, that means, in other words, it's 3 times some number. So n is some integer, I don't know what it is, but if it's divisible by 3, 3n is divisible by 3 because I can divide it by 3 and I still get n, which is some integer. So that's how we like set up this first part to show that this number that we have, the sum of the digits, is divisible by 3. So this is what we're showing here. Okay. So then we have to represent the number. That's the next part. So this entire number is a 4-digit number. So I can't represent this number as A, B, C, D, because that would be a product of A times B times C times D, and that's not what I want. A, B, C, and D are just integers. So in order to represent the number, the actual number, I have to break it apart into the thousands place, the hundreds place, the tens place, and the ones place. So for example, let's say I want to represent the number 4,872. If I was going to represent this number, I can't represent it as 4872 as A, B, C, and D because, again, that would look like a product, so I don't want to say that. But I can break it apart and say this is really 4,000 plus 800 plus 70 plus 2. So break it apart as far as the hundred or thousands place, hundreds place, tens place, and ones place. So that would mean that if my number A here is my first digit, my thousands place digit, it's 1,000 times 4. So 1,000 A. And then I'm adding on to it how many hundreds I have, which would be B in this case, so 100B. And then 10C, and then my lonely ones place D. So this represents, this is the whole number. Okay, so what we have now is I have A plus B plus C plus D equals 3N, and I have 1,000 A plus 100 B plus 10 C plus D. And so now what we're going to do is show that this is divisible by 3, knowing that this is the case. So we're going to use a combination of these two equations, kind of like a system. So what I would do is I would solve for D because it's alone over here. So if I solve for D, I would move A, subtract A over, subtract B over, subtract C over. So I'd get 3N minus A minus B minus C. And now I can make a substitution into my second, this is an expression, not an equation, but I'm going to make a substitution into D. Which gives me that. And I can do a little bit of simplification here. So I have 1,000A minus A, which is 999A. I have 100B minus B, which is 99B. I've got 10C minus C, which is 9C, plus 3N. So now our last step here is to show that that's divisible by 3. So I'm dealing again with this expression. And to show that something's divisible by 3, that means that I could factor out a 3 without having any issues with like fractions and decimals. So I can factor out a 3 and still have integers left over. So in this case, I can do that. So if I take out a 3 from 999, I get 333, 33b, and then 3c, and then plus n. So this here is an integer. Multiplying by 3 means that this is divisible by 3. So again, I know that process was kind of, at least at the start here, maybe a little bit confusing. We're going to do it again, kind of all at once so you can see the whole process. But this is definitely something that is really repetitious. We do the same process throughout every time. Like we set up the first part, we solve for one of the variables, we substitute in the end. We always kind of break up this number into these thousands and hundreds and tens in ones place. So it's really similar to what we'd be doing. So let's do it for the divisibility check for 11. Again, I didn't write here, but we're going to deal with the same 4-digit number. So we're dealing with A, B, and C, and D to represent the digits of that number. So what we're showing here is that the difference between the truncated number and dropping the last digit is divisible by 11, then the whole number is divisible by 11. So we have to start with this section first, like this is the known information, just like this was the known information here, that the sum of the digits is divisible by 3. So I've got these four numbers, four digits, A, B, C, and D. And again, like how I would do this is I would take, let me see if I can, so if my number 9751, what I would do to check this divisibility is I would drop the last digit and I would like subtract it off. So that's kind of what I want to represent. So I'm taking this number that I have and I'm representing it in this way. So this thousands place becomes now this hundreds place. So this starts off with 100A, 10B, plus C, and then I subtract my last digits, which is 10, which is D. And so what I know about that it is divisible by 11, that means that if I do perform that operation, I get 11 times some number. So that's the known information, but I also have to represent the actual number. Which the 4-digit number is really similar to what we did for step 2. We have, since we're dealing with a 4-digit number, I've got thousands, hundreds, tens in one place, so I'd represent it as 1000A, 100B, 10C, and then plus some ones place. So again, this is like the information that we had at the start. This is just the regular 4-digit number. So we're going to do the same thing, which is we're going to combine these two equations, and I would still solve for D because I think that's easier. So I would add that over to the other side or get it by itself and maybe subtract the 11 over. So I'd be having 100A plus 10B plus C minus 11N equals D. And then I can make that substitution into my second equation, second expression. So I'm going to do that down here just so I have a little bit more room. So I have 1000A plus 100B plus 10C, and then D is going to get replaced with this 100A plus 10B plus C minus 11N. Now I can combine like terms. So I've got 1000A plus 100A, which is 1100A. I've got 100B plus 10B, which is 110B. I have 10C plus 1C, which is 11C, and then minus 11N. And again, the last step that we have, now we're on step 4, is to show that that number is divisible by 11. So then we can factor out an 11 to make sure that this actually does make sense. So if I take out an 11, 1100 divided by 11 is 100. 110 divided by 11 is 10. 11 divided by 11 is 1, and then minus n. So because, again, we can like factor out that 11 and it's good to go, we are not left with any decimals or fractions or anything like that. That means that it was divisible by 11. We're getting an integer, so yes. It's divisible by 11. So I don't think there are 2 in your homework like that. I think it's 8 and 9. So that's dealing, I think, with the divisible by 9 rule. And again, like I think it's easier to like follow it with these types of steps. Use maybe this example, number 4, to help you and help guide you in that process. But again, it's very similar. It's very procedural. We do a very similar thing every single time. We have to start with this known information. We have to express the digit. We combine these equations, and then we show that it's divisible by whatever number that you're actually showing.